Good evening once again. So today we will look at logistic regression. If you remember last week, we had already started off with regression. In fact, last week we went into regression, or the week before last week we did a bit of revision. So we looked at linear regression. We looked at with a single variable using a normal function, a normal equation, which was just using a mathematical equation to solve it. And then we looked at linear regression with a single variable using gradient descent. So in that, we explained gradient descent and we understood what gradient descent means and how it makes it much simpler when you have a lot of parameters for you to be able to still do that linear regression. And then we looked at linear regression with multiple variables, where instead of having a single x, you now have x1, x2, x3, and so on. And instead of having a single m, that is the coefficient of m of x, rather mx plus c, you now have multiple m's, which you could also notate as m1, m2, m3, and so on. So those m's, right, are in traditional mathematics, they are called coefficients, right? A coefficient of a linear function or a linear equation. Those are the coefficients of x, right? So in machine learning, we call those same coefficients, we just call them parameters. So even though in machine learning, parameters is not just the coefficients of x, but it also incorporates the constant c, which you could also give it any other name or any other notation, right? You could make it B, you could make it beta, whatever, right? But we know it's a constant. A constant is actually a coefficient as well. The only thing is that it is a coefficient of the number one. So if you were to write out your linear equation, in a generic way, which I showed last week, you would write it something like this. You would write it as M1. So let's assume that we now have a lot of x's. So instead of just one x, you have a lot of them. So you now have M1, right? X1, okay? Or M1 dot X1. Let me use the dots to represent the multiplication, right? Which is kind of standard. M2, right? Dot X2, right? And you just continue like that until you get to generically Mn, which is the nth M, right? The nth coefficient dot the nth value of x. But we also still maintain that c function, that c constant rather. Okay. So now what we do is this c is actually, if you expand it, it's actually c times 1. So just like m1 is a coefficient for x1, m2 is a coefficient for x2, right? And so on. Mn is a coefficient for xn. So c is a coefficient for 1. So when you multiply anything by 1, you get back that same number. And that's why it is c times 1. So what we do now is we take this constant and we take it to the beginning. And instead of calling it c, we call it m0. So we now call it m0. And basically, that is the same thing. So all of these numbers, all of these coefficients, m0, which is a coefficient for the number 1, where the parameter is actually 1, right? It has a constant value of 1. Sorry, the independent variable. It's not really a variable. It's just a constant with a constant value of 1. So this is now like the coefficient of it. So, but we don't really, put it that way. So it's M0 and this is M1 and M2. So these coefficients, right? When you now take them out, you can now have um a vector, right? A vector of parameters. And a vector is simply a list of numbers from a mathematical standpoint or a programming standpoint, right? It's just a list of numbers. So we now have this vector of M0, M1, M2, M3, right? And it just continues like that until you get to Mn, right? This vector is a vector of coefficients. This vector of coefficients is what we now call parameters. Those are the parameters of the equation, right? In this case, it is a linear equation, but with multiple variables, right? There is no quadratic element to any of these variables. In other words, it's not raised to power 2, which would make it quadratic. It's not cubic. There's no x that is raised to power 3, right? So these make up your parameters. So if you actually back up, right, to the previous slide where we did multivariable, you actually see this same thing I wrote in a generic form. And this is it. It is now in a generic form. And we're going to go into some of this when we talk about the vectorization. So I just want to show you the generic form. So this is the generic form, right? Uh, yeah. So in this generic form, you now see that instead of using M0, M1, M2, like I did as the letters that represent the coefficients or the parameters, here they're using beta, right? So you have beta 0, beta 1, beta 2, beta n. There's also another one here called epsilon, but this epsilon is just a small factor that is used to kind of handle or take care of noise, right? So this is the general formula of a system of a single linear equation that has multiple variables. So we'll talk about logistic follow-up to the linear regression. So what is logistic regression? Logistic regression is still linear regression. The only difference is that logistic regression also uses multiple variables. You could actually also do a single variable logistic regression. Maybe we can try that. But a logistic regression is used for classification. And why it is called logistic is that it does not predict a number, right? It does not try to predict the value. Rather, it tries to predict a classification, right? It models the probability of a binary outcome, right? So typically, binary outcome in this case means that you can have one of two values, right? Either 0 or 1, either true or false, either yes or no, right? Either good or bad. You are trying to ch- choose between one of two options, right? So the model is trained to choose between one of two options when you give it the particular set of inputs, right? That is logistic regression. So effectively, logistic regression is just linear regression with where you use the line as a decision boundary, not as a prediction of a specific value. So if I go back to our, you know, we did a drawing some time ago, and I'm going to go back to it, where I showed you the regression line and how you can play around with it. This is the regression line, right? Now, in this regression, you're trying to predict specific values of y given a specific value of x. Okay, so you're given x4 and you want to predict the y4, which is y hat 4, right? But in logistic regression, given this x4, we're not trying to predict the actual value of y, but we're rather trying to predict whether this y is above this line or below this line. That's why it's called a decision boundary, because this line becomes a boundary that you can use to decide. If it is above this line, you can say that anything above this line is a yes, right? So that is the positive. And then anything below this line, you could say is a no, and that is a negative. So using this alone, you have used the same line both for a linear regression problem and a logistic regression problem. So the logistic regression problem is now anything above this line, right, is considered a yes or one or true or positive or good. And then anything below this line. So remember, this is the line. So the line, anything below, no matter where it is on this line, right? Or sorry, on this side of the line, it doesn't matter where it is. It can even be negative on the negative side, right? This way. But as long as it is on this side of this line, right, it is classified as no or zero or bad or negative. But if it is on this side of this line, then it is classified as yes. This is simply the difference between a linear regression and the logistic regression. So um, let's now go look at, even though this is not perfectly the explanation, if you want to draw a logistic regression line, you would first of all do this linear line. Then this outcome here, you pass it through a, well, let's say a function that will clearly, you know, differentiate it or separate it into 0 or 1. And we're going to see what that function is. It's actually called a sigmoid function. So that is what logistic regression is. So it has three main components. The first component is a linear predictor, which is the same as a straight line equation we have been dealing with since, whether it's a single variable, right, or a multivariable. In this case, we actually have this W as a vector, and this X is also a vector, right? Um, what we are saying effectively is that the um, this represents um, a number of data points. We are going to look at that. I'm going to also kind of break that down later on when we're talking about um, vectorization. But for now, we just see it as we can consider the W. The W is now what we were calling M, right? Or beta or theta, right? It is the parameter. The only thing is that we are now looking at W as a number of them. It's not just a single W. And I'm going to break that down when we go into vectorization. But even for the purpose of explanation, right? So that we take the step, you take it step by step. We can look at this W as a single value for now. If we look at it as a single value, this T, this is not really a T though, even though it looks like a T, it means transpose. So W is actually going to be a vector that you would transpose or a matrix that you would transpose. Okay. While the X is still a vector that contains all the X values, right? Or a matrix that contains um, the different X values, the different data points. I'm going to explain how this becomes a matrix and how you can determine what does the row mean and what does the column mean in this matrix. And then the B, right? You can now say that what we were calling C, which is a constant, we now call it B. So effectively, we have moved from the mathematical notation that we used when we started, right? Which was referring to the straight line equation y equals to mx plus c. We have now moved from that to using a more machine learning, traditional machine learning notation, but it's still the same thing, right? It is still a linear equation or a system of linear equations. So this is still the same equation, even though there's more inside this, which I will unlock very soon. But this is just the first part of it. And that's why it's called a linear predictor. So it's still a regular linear regression line. That's what this is. But it's a predictor, so saying the value. Okay, so but that's the first part. Then the second part is you now take this predictor and you pass it through a probability function. So the probability function would now turn the Z value, which is the outcome of MX plus C or WX plus B, W transpose X plus B, to turn it into a binary value. That's the main purpose of this function. And if you look at this, this is the Greek alphabet, the Greek letter sigma, right? So that's why this function is called a sigmoid function. It's called a sigmoid or logistic function. And its purpose is to make it clear whether the value of Z is closer to 1 or closer to 0. That's the main purpose. And this is how it is implemented, right? It uses the E function, which is the exponent uh, function. This exponent is actually a number. I think if you look at it, it's actually a number. So for those who are a bit more familiar with mathematics, it's used a lot. It's used a lot in calculus and a whole lot of, different mathematics. It is at the center of mathematics, this number, right? You can use it to represent logarithms, sines, cosines, and complex numbers as well. So this is the equation for sigmoid. I'm not really going to try to explain to you how we arrived at 1 over 1 plus e raised to the power minus z. I'll only show you, well, okay, I have a Jupyter notebook I will use to show you how the curve looks like and why it is used, right? But note that the z that is used as the negative exponent of this e is the same z, the value you get when you have done this first linear prediction. Okay, so you can see it in this way. You can effectively see it as a two-step thing, right? In the first step, we have a linear equation. I'll just represent it with a single linear equation, right? So we'll have the same single linear equation. That's the first step. Then the second step, we take this single linear equation and we stuff it through this sigmoid and we get a different thing. So if you look at a sigmoid function looks something like this, and we're going to play around with it a little bit. But it looks something like this. I'm going to sketch it, so my sketch may not be very nice. Um, it looks something like this. This is kind of how a sigmoid function looks. And the reason why it is very sharp point in the middle. On the x-axis, you have some values. Okay, maybe 0 here to 1. Then what's happening, or 0 to let's choose a bigger number, maybe 100. So you have 0 to 100 here. At this threshold point maybe it's halfway. So maybe 50. Okay. So at this threshold, you can see that the value rapidly changes. To the left of this threshold, the value of y, so let's now call this y, while this is the intermediate value, which is z. So technically, this is also z. We're now taking z and we're plugging it into the sigmoid function, which is what you have here. So you have z here. This is x. So this is x, a linear function against z. So you take this z and then you plug it. That's the first step is to get z from x. Z, plug it into this, and you get but you notice that the value of y is going to be very low. I will continue to remain low, right up as low as this. It won't get higher than this value until you get to this point. Then at this point, you now have a rapid section where it rapidly changes from this very low value to this very high value. And then beyond that point, it now sticks on this very high value. Okay. So you see that Y is typically going to be either very small or very large. Even though there is a section here where Y will be in between, but this section is so small, right, on the Z side of it. So there won't be a lot of times or a lot of numbers that will be in this section, right? This is what a sigmoid function does. So what it does effectively is that the sigmoid function is going to transform this linear equation into a, a more separated, either it is 0 or it is 1, or either it is very close to 0, right? In this case, where Y is really close to 0, or it's very close to 1, where Y is really close to 1. So of course, Y is actually quite close to 1 up here. So the interesting thing with the sigmoid function is that the value of Y never exceeds 1. In fact, it never gets to 1. If you look at the maths of it, because if Z approaches infinity, negative infinity is very small, so E approaches 0, and you're going to have 1 over 1, which is 1. So as you go to a positive infinity for Z, the value approaches 1. But if Z approaches negative infinity, so this will be plus infinity minus negative infinity plus infinity, which is a very large number. In the limit of it, this will be basically a very large infinity number. 1 over infinity is a very small number which approaches 0. So what it means is that as you also approach negative infinity, the value of Y approaches 0. So that is why the sigmoid function constrains your output to always be between 0 and 1. And is always very close to 0 or very close to 1, right? That's why the sigmoid function is very, very useful for logistic regression, because it means that you can force your output from your model to always be either 0 or 1, which is what we said here. This is where we started from. We said that Y has to be either 0 or 1. So if you use it as your model will be very close to what Y is, right? Irrespective of what the intermediate value, which is Z, is, okay? So that's what this is. Basically, you can summarize it by saying that the sigmoid function gives you the probability that Y equals to 1 for any given value of X, right? The probability that Y is 1 for any given value of X. If the given value of X is 0, then Y is likely going to be 0. So the probability that Y is 1 is going to be very low. Basically the same thing as the value that you get from the sigmoid function, right? But if on the other hand, your X is very high and you plug it in here, then the value of a sigmoid function is telling us that Z, which is intermediate value that comes from here, is going. So the probability that Y equals to 1 is also the second piece. Now, the third and most important piece is, remember, whenever you're training any regression model or any model for that matter, you have to have a loss function. The loss function is what allows you to calculate how far away your model is from what you actually want it to predict. If you don't have a loss function, you cannot train a model, right? There are two things you need, the loss function and the gradient equation, the gradient function. So the loss function here uses what we call a negative log likelihood or binary cross entropy. Right. I can go into a bit of explaining how this is a piecewise equation that combines two parts. And I'll see if I can explain these two parts. So the first part of it is this one, right? And then the second part is this. Let's look at plugging in some values. So the way this works is this. You can say, in fact, let me do this where I can write better. Let me do this in the Excalibur. So I'm going to I'm going to take this, or I'm going to take this, and I'm going to go back to my, and I'm going to go a bit to the right. And I want to explain this. So this,
Please mute your mic.
so this is the piecewise equation that we call the binary cross entropy. It's piecewise because it has two sections. It has the first section, um, this section, and then it has a second section, which is this section. Now let's look at the first section. The first section is take the value of y and multiply it by the value of ln of p. So yi, right? Take the value of yi and multiply it by ln of p. So for those who are not very maths inclined, ln is natural logarithm, so it's just a log. And what it means is that what ln does in this case is that it either gives you a 0 or a 1. Okay. So remember the values, if you remember what we said, if you remember this, the values, the outcome is always between 0 and 1. So let's simplify that way. Forget about the values in between. We have used a sigmoid function to make sure that you rarely see the values in between 0 and 1. So for the sake of simplicity, let us just go with 0 and 1. So we have 0 and then we have 1. Those are the two possible values. Now, what I want to do is this. If you look at 0 and 1, the two numbers that we have here, okay, let's start with the case where it is 0. And then, so let's look at the equations. When x equals to 0, if you remember our line that we drew, maybe I'll draw it again. Let me just draw it again. If you remember our line, all right, the equation and the decision boundary. So this is a line. And we're just using a single linear equation here just to make it easy to understand. So if you take the single line, so let's only take 2 points when x is 0 and when x is 1. So when x is 0, y is also 0. When x is 1, y is also 1. We'll just go with um, that simple case. There may be other slightly different cases, but we're trying to calculate the cost function or the loss function. So when x is 0, y is equals to 0. So in this situation, right, if your y hat, which is your prediction, and I'm going to just leave it at that, is not 0, maybe if it is 1, then what we are saying is that, remember the y hat or p, in this case, p is a y hat. So your prediction is p, that's the probability. In linear regression, we use y hat, right? But here we just use p. It's the same thing, right? In fact, in some situations, we'll still use y hat. So p is a prediction of your model, while y is the actual value that you're trying to predict, or the true value you're trying to predict. And you can see here P is W transpose dot product X. X. Basically, think of it as MX, right? Or MX plus C. And then you pass it through the sigmoid function. So a sigmoid function is going to straighten it out the way I showed you. So it's not going to be a straight line, but it's going to be a function that quickly changes from 0 to 1 in the middle of the pack, right? So you have X, when X is 0, Y is 0. Now let's assume your model was predicting 1. This is now a case where you have a model that is not doing very well and is predicting 1. That kind of model would probably be something like this, right? Because if your model were reversed this way, okay, it means that if you had a data point, so we can also bring in the data points. So if I have my actual data point, this is X is 0. Okay, we'll use a different thing for that. And then, yeah, so this is the real data. So what is happening here is that this is the real data, but your model is doing wrong prediction. Because according to the prediction, this one should be 0, right? This one that where uh, X is 0, Y should also be 0. And this one should also be, when X is 1, Y should be 1. So that is correct. Your model is off. So, but since this is a decision boundary problem, a classification problem, you're not predicting actual values. Because if we were using normal mean square error to calculate the loss, that would make the loss too big in some cases. But we just want to know how far is it. So what we do is we use this piecewise. So the first part of this piecewise is saying, if y is 0, right, I am supposed to predict 0 because y is 0. So if y is 0, then pi should be 0. And if pi is 0, then the log of pi is log of 0, right? And log of 0 is infinite, right? 0 doesn't actually have a log. Okay, 0 doesn't have a log. So what we are saying is that, but the way this math works out is that this value will end up being 0 because 0 times anything is 0. So it's kind of just going to ignore this, right? Um, that is whatever the prediction that you have here, this 0 is going to nullify it. So this particular part of the equation, a piecewise equation is an equation that is made up of two parts. And you typically what you do is in a particular set of conditions, one part of it will be nullified and be 0, no matter what the value is, while the other part of it will be the one to um, you know, to prevail, if I may use that terminology, right? Then in another set of conditions, right? The other one would be the one that will be nullified while this one would prevail. Now, in this case, whenever yi is 0, this part of the equation will be basically nullified. So the only part of the piecewise equation that would matter is this one, where it's 1 minus yi, because yi is 0. So 1 minus yi is 1. And 1 times anything is that thing. So effectively, what we are saying is that when y is 0, we are only going to look at ln of 1 minus p. So whatever prediction it is, we subtract 1 from it and take the natural logarithm of it. That is going to be our cost function when y is 0. But when y is 1, then this second piece, right, disappears because 1 minus 1 is 0. So 0 times this. So it kind of disappears, right? It's nullified, and this one prevails. So effectively, it is a piecewise equation. That's how you should look at it, that you can interpret this way. This one only matters when y is 0, right? sorry, when y is 1. So it basically says when y is 1, you use this part, okay? But when y is 0, you use this part. That is effectively what this equation is. So now, since we have, um, simplified it that way, when y is 1, right, it's saying use ln pi. Okay, let me put this in brackets because I don't, even though Excalibur has a mathematical thing, but it's not activated here. When y is 0, use ln 1 minus pi. So this is what it is telling you. It is a piecewise equation that is made up of two parts. The first part is when y is 0, you use ln 1 minus pi to calculate the cost, sorry, the loss. But when y is 1, you use ln pi or ln p to calculate the cost. Now, so that leaves us with the question, what is ln p? Because that's really what matters, right? Ln p is just a logarithm of the prediction. And we've already seen that if p is 1, then the ln is 0. If p is less than 1, then the ln is negative. That's a natural logarithm, is negative, right? And if p is 0, the ln is infinite, negative infinity. So what this will give you, right, is going to be a curve that looks like this. The ln of P1 curve is going to look interesting like this. Um, so let's start again. The ln of P, but let me just remove the I, because what we're saying is the cost function. The I just means for each item, for each data point in your data set, for each row in your data set, okay? When Y is also let me put this here so it's also easy. When y is 1, use ln p to calculate your loss, right? Or let me even just put it this way, loss equals ln 1 minus p when y is 0. That's what this is. And when y is 1, then loss equals, remember, loss is the error of a single data point. When you now combine it, you now have the full cost. And that is what this whole thing does with the sigma function. So that means that for data points that the real value is true, sorry, yes, for data points that the real value is true or 1 or yes, right? The loss for those data points is calculated using the logarithm of whatever prediction came out from your model. But for data points where the true value is 0 or false or no or negative, right? The loss for that single data point, right, is the logarithm of 1 minus whatever the model predicted, right? So what does that mean in real terms? Let us even look at the curve of ln p. So the curve of ln p is basically a log. So let me see if I can sketch it. It's basically a log, right? And this is how log looks like. Something like this. That's kind of how, this is not perfect though, but that's how a log function looks like. Okay. And then 1 minus log, ln of 1 minus p is essentially flipping it, right? Basically flipping that. So um So that curve of 1 minus x, right, or 1 minus p. Let me move this a bit to one side. Will look something like this. So intuitively, we would have thought, okay, it should look, but it looks a bit, yeah, it looks a bit like this. Um, it looks a bit like this, right? Something like this. Maybe not very uh, specifically like this, but it looks like this. And sometimes it crosses here or it crosses here, you know. So this is how it looks like. So if you look at these two, which would be saying, okay, this is the equation of a lane, and this is the equation of a um, lane of 1 minus p, then what you say is that this is how this is the loss. This is what you use to calculate the loss function, right? For when the value is the real value or the true value is false or no. But when the true value is 1, right? Or the actual value is 1, this is what you use. So that's just it, right? And um, and why this is very helpful is this. When the value, when y is 1, right? That is the actual value is 1. That means um the loss will be high. Well, this is actually a reverse. Usually what this does is that if your probability is, let me place this the way they should be so that it's easy to understand. Because the whole idea is that the loss should be small when the value predicted, when p is close. Okay. So if y is 0, okay, yeah, if y is 0, oh yeah, okay, I think I mixed it up. Sorry. Yeah, when y is 0, um, okay, when y is 1, this is the loss is calculated with this. When y is 0, the loss is calculated with this. So we are still correct. Now, ln of 1 minus p actually looks like this, okay? Meaning that it is going to be 0, okay, when y is 0. But when y is anything else, sorry, when x is 0 or when p. So let me also clarify so that I can put this on uh, this is p, right? This is p, which is the prediction, and this is y. So this is essentially the function that you use this is the cost function. Okay, so let me not call this y. This is L, which is a cost function. Or yeah, it's a cost function, or the loss function in this case, because we are just looking at a single data point. So if my prediction, right, is far from 0, the loss will be negative and will be very high negative value, right? Um, but if it is at 0, it will be 0. If it is also, it's kind of like this. Let me draw this thing properly. So this is how this curve is. So if my prediction, which is a P, is here, as a matter of fact, if it were even possible for us to extend this, right? This is not a very good approximation. It's actually steeper than this. I think I want to keep it the way it is. It's kind of like this. So what it means is that when P, right, the value of P is high, you have a very highly negative value for loss. But you have a value of loss that is 0 here. So you see that the value for loss is going to be negative when P is far away. Again, remember this is when y is 0. So this is when y is 0. When y is 0, you want your p to be close to 0 right here. So when p is close to 0, right, according to this graph, the value of y is the value of L, sorry, which is a loss, is going to be 0. But when p begins to go positive and increase, you can see that this begins to go down. And that's why this is called a negative log likelihood, because it actually goes in the negative direction. The value of the loss goes negative, becomes very big, right? And that's why you need this negative sign here. But what this negative sign does is that it will convert this negative log likelihood into a positive value. So what you are actually calculating is not ln 1 minus p, it's actually minus ln 1 minus p, which is the negative of this. The negative of this is essentially flipping this thing around. So maybe I should flip it around so it makes more sense, right? Um, so when you flip it around this way, you can now see it makes a bit more sense in the sense that when the loss is close to 0, right? When the loss is close to 0, sorry, when the probability is very close to 0, the loss will be close to 0. But as the probability begins to go out this way, you see that as this curve is going up, the loss is also increasing. So this is the piece of the equation that you use to calculate the loss when the actual value is 0. You can see there are three factors there: the loss itself, the predicted value, and the actual value. Now, this is the equation you use to calculate when the loss, when the actual value is, you know, um, is positive. So I did not draw this curve very well. This is actually the curve, the exponential curve, which is e raised to power x. The actual lean curve is more like this, right? So I did not draw this well. So let me draw it properly. It's actually a negative uh, curve that starts somewhere, right? And, it's, let me bring all this. It passes through at x equals to 1. So the interesting thing is that when the loss is 0 when p equals to 1, because ln p is 0, right? And then it keeps going. But this is a positive value, okay? Now, remember you have a sign here. So when you have a sign, that means we flip it. So if we flip it, okay, you now have the same thing, but this time around, it looks something like this. It still crosses the line at this point, okay? So what's happening is that when P is at 1, the probability is at 1, which is, remember, this is the equation we use to calculate the loss when the actual value is 1. So in that case, when the probability is 1, which means it is close to the actual value, then the loss is 0, which is this line. But when it begins to move away from it, right, the loss begins to become a large negative value as well. So that's the interesting thing, right? It becomes a large negative value. And if the probability becomes lower than 1, okay, the loss increases, becomes a large positive value. But here's the thing. Remember that the value of P is probability. And we already saw that, first of all, we know that probability cannot exceed 1. Value of probability is always between 0 and 1. So what that means effectively, like this part of the curve, right, after 1 does not really come to play, right? It doesn't exist in this context, right? And because we're using a sigmoid function, it also basically does not, so you can just look at it this way, that we end up with a curve that just stops at the point where p equals to 1, because p can never get above 1. So you now have a curve that goes this way. This is not perfectly what I wanted to do, but it's close enough, right? It's close enough. Okay. So what we are saying here is that When P is at 1, when probability has 1, right, the loss is 0. But when probability goes towards 0, the loss goes up towards infinity. Same thing here. When probability is at 1 here, the loss goes to infinity. Okay. And similarly here also, because probability can never go below 0, this section of the curve below 0 does not really come to play. So it kind of stops here. So you now have a situation where when the probability is at 1, let's assume this is 0.1, it becomes infinite. But when the probability, and when I say probability, that is the prediction from the model. When the prediction from model is at 1, it is very high, the loss is very high. And when it is at 0, the loss is 0. So you now have these two, these are actually symmetrical. So don't mind the way I'm drawing it because I'm not using a very good. I could actually do this with a graphing program, but I'll show you how that works. To increase exponentially. Similarly, when the predicted value is 1, if the value we predict, sorry, when the actual value is not 1, when the actual value is 1, the value we predict, if it is not 1, you can see that the error also increases. So this is how you can look at this binary cross entropy. And that's why it is called negative log likelihood, because it is likelihood is based on the logarithmic, which is the natural logarithm, and it is negated. If we did not do this negation, then we wouldn't have had this. We would have had this thing looking this way. We would have had this one also looking this way. So the negation is what makes it useful as a cost function or a loss function. So I hope I spent a bit of time on that, but I just needed to do that so that we can understand how the whole thing works. So that is the summary of this. So this single function is for a single data point, right? Again, let me recap. If the true value is 0, then if the predicted value, which is P, is not 0, then this loss will be very high. And this one will be 0 because the true value is 0, right? But if the true value is 1, which is this one, and the predicted value is not 1, then the loss will also be very high. So that helps to combine and give us a proper understanding of the loss. And they said the loss is convex in W. A convex function is a function, well, that is shaped like a bowl. Let me simplify it that way. So that's how you do the cost function. Those are three elements in logistic regression: the function itself, the model, which is made up of a linear predictor, and the probability, which comes from the sigmoid function, and then the loss function, which comes from the probability, which is the P, right? You use the P and you plug it into this negative log likelihood or binary cross entropy equation. So with this, you use the standard process to fit or to train on logistic regression. You use batch gradient descent, which we already talked about. You use the entire data set. You use stochastic gradient descent, and you can use mini batch. So mini batch stochastic gradient is for each epoch, you use a single data point to train. While for batch gradient, for each epoch, you use the entire data set to train. While a mini batch is somewhere in between. For each epoch, you pick a subset of the data set and you train. Then the next epoch, you take another subset and you just keep going that way. And then there are a bunch of other ways as well which you can do training. Um, these are other things. We've talked about gradient descent. So there's a bunch of others like Newton. There is a quasi-Newton, coordinate descent, trust region, and all of that softmax. Then we also have regularization. We'll talk about regularization a lot more later on. Um, so those are the methods um for logistic. Now we've talked about the loss function, but remember I said you cannot train a model if you don't have a loss function and what? The gradient. So we need to get a gradient. The gradient is basically this is the same thing as I've just shown. The prediction is a sigmoid, right, of XW. XW is just MX, which is parameter times value. Okay, parameter times value, you pass it through a sigmoid function and get the probability. This probability, you pass it through the negative log likelihood, which is 1 over n times the summation, right, of these two, right? The summation of this, which is y transpose ln p. This is when the true value is 1 plus 1 minus y transpose ln 1 minus p, which is for when the actual value or true value is 0. So this is a loss function. We just looked at it. So the gradient is actually, interestingly, the same formula that we use to calculate gradient when we're doing linear regression, right? It is still x times the loss. Remember, the loss is p minus y, or the error, right? This one is now not the loss function per se, but the error, the difference between the predicted value and the real value, right? So you now see that there are two types of loss here. You have um, loss based on this, right? Which is a NLL log, negative log likelihood, or binary cross entropy, BCE, right? But there's also the loss, the simple loss, or what we call basically the difference between the predicted value and um, the true value. We multiply by x and divide it by n. So this is still the same thing we were using for linear regression, is the mean of the difference in the values. Then there's something we call a Hessian. We're not going to look into that in detail. So this is how you do the this is how you do it's still the same steps, right? It's still the same steps that you use for training logistic regression. Okay. So same thing. Step A, you prepare your data, right? When you prepare the data, you add a bias term. So a bias term is column of ones. We're going to talk about this in detail. Remember, I just talked about that. The bias term or the constant, right? You can consider a constant as a coefficient of ones, right? And then you need to do one hot encoding. Because for categorical features, they can only be true or false. They cannot be actual values. So the one hot encoding is a way to convert it. If it is labels, for example, true or false, you need to change it to numbers. Remember, everything has to be encoded. So you need to change true to 1 and false to 0. Okay. And so on. Feature scaling. Um, if you need to do scaling, we'll talk more about that. Then you shuffle the data set, you do your split into train and test and validation. And that's the first step. Then after that, the next step, this is just a training loop, which we have already done. Initialize your weights, choose your learning rate. Okay. And you can choose from 0.1. If it is too much, you go to 0.01. If that is still too much, you go to 0.001. And then you choose your optimizer. For now, we're using gradient descent. And then you can do regularization. We're not doing regularization for now. And that's how you go. Then you calculate the iterative update. You calculate the gradients. You calculate the logits, the Z values. You pass it through the sigmoid. Okay. And then you compute the gradient. Okay. And then after computing the gradient, you do the update. Okay. And that's it. So it's what we have been doing before. So those are the steps for logistic regression. It's the same as others. The other things like stopping, validation, post-processing, which are generic training methods. We're going to talk more about those. So with this, I want to just quickly go to show you logistic regression. So yeah, I'm going to share this. I think I've shared this already, but I'm going to share this again. It's a statistical method. I think we've talked about this, so I don't need to go through all of this, right? You have a sigmoid or logistic function. So this is the most important thing. When you're doing logistic regression, you have to pass your prediction or your linear what I call the linear combination of your inputs, right? You have to pass it through the sigmoid function. So this is kind of how we do it. So of course we start off with NumPy. Um, NumPy allows you to plot graphs. Then here I try to show the three components. What I just did before, the three components of the two components of the sigmoid, right? So this is the two components of the sigmoid because sigmoid is or let me not say components, but the way the sigmoid kind of transitions from just an exponential function, right, to the sigmoid function. So we start off with an exponential function, which is y equals e of x. Okay, that's what this is. This first function is y e of x, right? Y equals e of x, e raised to power x. That's what this is. Okay. Then after that, we now do y equals e of minus x, and that gives us this. So that's y e of minus x, that gives us this. And then we do the sigmoid, which is a flipping it, taking a reciprocal, adding and taking a reciprocal. So the sigma gives you this, which I had already shown. And the steepness of this middle section, you can control it by adding a constant to the z. So, and that constant is this c. So you can see this is 1 over the same thing that we have here, right? It is 1 divided by 1 plus. You have to put the lower part, the denominator, in brackets. Otherwise, your equation will not work. So this denominator is in brackets. But you can still see this numerator is 1 divided by, which is what we have, 1 divided by all of this, right? All of this, we have to use brackets. So in these brackets, we now have 1 plus NP. NP is NumPy. So we are using the NumPy exponent function, which is just E, right? So this exp is the exponent function minus c times x. So remember the exponent is to minus c times x. This c is normally 1. So if it is 1, you see that it's just minus x or minus z. But we can use this c to kind of control the steepness of this section. That's what I was trying to demonstrate here. So if you look at this, you will see that with a value of c of 2, you can see how this becomes very steep. I can actually change this to a lower value, maybe like 0.5, and I run it again, and you see it is smoother. It's a bit gradual with a lower c, right? But when you increase, C is 1 is a normal standard one, right? And this is a standard sigmoid. If you increase C to 2, you see that it gets sharper. If you increase C to 20, which is a very high value, it becomes very steep, right? So that is just how you can control that. But in most cases, you don't need to do that. So I've already explained the negative log likelihood equation or the uh, binary cross entropy, the fact that it is made of two pieces, right? The first piece, which is a minus ln p1, right? Minus ln pi, which is what I just did, when the actual value is 1. So when the actual value is 1, this one disappears while this one remains. This one is just 1. So you end up with minus ln pi. And then when the actual value is 0, remember the actual value is the value you are trying to predict. Okay, that's a y. So when the actual value is 0, then this part of the piecewise disappears, and this part remains because 1 minus 0 is 1. So you just get a ln of 1 minus p. And I had already shown you those two equations, how they actually look like. We could actually plot them here, but I think I have shown you that. how it looks like. This is the plot of it. So when the actual value is 1, you can see it goes this way. When the actual value is 0. So what this means effectively is that when the actual value is 1 and your predicted value is 1, then your loss is very small, which is what we want. But if your predicted value is closer to 0, which is down here, then your loss will be very high, which is what we don't want. Conversely, when the actual value is 0 and your predicted value is 0, you are close to the predicted value, so your loss is 0. But if your predicted value is 1, which is very high, then your loss will also be very high. So that is how you can intuit that aspect. And this was just to plot so that we can see that. So the gradient, like I said, is essentially just predicted value minus actual value, right? Times the x, just like what we have been doing before. Predicted value minus y minus actual value for each data point times x. That's it. So you can then sum this product and divide by n to get the mean. So it's still the same thing, right? And this is the non-vectorized case of it. I'm going to talk about vectorization shortly. So, so for a large data set, right? This is something I need to explain. I'll come to this. Maybe we'll just end it that way. But before I come to that, let me show you the difference between the logistic regression and the linear regression. We did linear regression with two variables, okay? And when we did linear regression with two variables, we used a very simple, I'm going to extend this classwork and show you what happens when I do that. So here we're just trying to predict, right? We're just trying to predict. So this is regression. Now we could turn this into a classification problem also. And the way I would do this is I'm going to put this in, import NumPy and matplotlib, and then I'm going to put this in. Okay, so that's NumPy and matplotlib. Then I'm going to just plug in these values. So we still have the x and the y. Now, we still have a standard um, two linear equation to predict. So before we were saying y equals mx plus c, m times x plus c. Okay, so we'll start with, let's make some values for m and x. Sorry, m and c. So m, we can just start with a value of 0.1 and c equals 0.1. Okay. So y equals to mx plus c, but this time around I'll use z because z is used for the intermediate value, which we call the logit. The logit is the value, and it's still the same thing, right? It's still the same thing, except that we would have stopped at this point for a linear regression. But because it is a logistic regression, we have to pass it through a sigmoid function. So now I will define the sigmoid function so that because it's a bit involved, we can just use z here. So the sigmoid function is this 1 over 1 plus np exponent z. That's the sigmoid function. Um, yeah, so if we wanted to use some mathematical notation, it would be um, one um, 1 plus um, exponent. So this is, yeah, well, this is LaTeX. I probably have missed some. Okay, I've missed some. Um, anyway, let's move on. I'll need to correct that. So this is the sigmoid function, right? So we can now say P, if we follow that notation, which is a probability, should be this sigmoid function times Z. Okay. So if we now look at the actual value of P, you see that it's actually probabilities. So the Z had values like 1.1, 1.0, values that were above 1. But you see that here they are never above 1. So sigmoid has scaled everything to being inside um, 0. Now, to do the negative log likelihood, which is the cost function, right? Yes, you can say log loss. Okay. You are going to do um, remember the negative log likelihood is 1, right? There is this whole epsilon thing, which I'll explain later on, but for now, let's ignore it. It's going to be y, right? Y times y pred, okay? So let's just say or y hat. Let me use y hat. So y hat is a predicted value or p. Let's use p. Let's use p. So y and p. So I'm going to talk about this whole thing later on. But for now, let's just it's just going to be minus NP. So remember, it has a negative sign, and it's the mean of y times NP log P, log of P. So in NumPy, log gives you the natural logarithm. Then 1 minus y, which is a part of it when y is 0, log 1 minus P. And that's it. It's as simple as that. So we have our negative log likelihood. The reason why we need epsilon is because if you take the log of a negative number, it is infinite, it's very large, and it will cause problems. So that's why we need a small number to add to it so that it will never get to 0. Also, if P is 1, then 1 minus 1 will also be 0. So you also have a log of 0 here, which is um, a very high infinite negative number, right? Again, it can cause problems with your code. So we also try to ensure that this does not get close. It does not get to be exactly 1. So that is the essence of this, right? For your information. But I'm just simplifying it now so that you see that this is the same thing as the equation which we had used here earlier, right? So just for the information. Okay, so I was trying to paste that image, but it doesn't look good. So let's forget about that. Good. So we have the 3 components. Okay. The first component of it was the, like I said, the first component is the prediction. Now we have the loss. Now we need the gradient. So the gradient is the same as what we did before, basically. In fact, you can simply calculate the gradient by just saying y minus p, right? Y minus p times x for each x. So we don't need to overthink it. That's a gradient. So with that, we can do a training loop. The main difference we have introduced here is 2 things. One, we have introduced a sigmoid, right? As far as, comparing this with normal linear regression is concerned. We have introduced a sigmoid, okay? That's one. And then secondly, the loss function is a bit more involved. It's not that yp dot mean of square error that we're using before. So we can still do the same training loop. Everything else is the same. You can specify your learning rate, right? You can specify your epochs, maybe 10 epochs, and we can just start and say for epoch in epochs, okay? You first of all do your Z. So yeah, so we see the two steps here for you to calculate the prediction. Okay. Um, Calculate the probability or prediction, which is NP dot XM. Well, I'm not going to do this because I'm just doing a simple thing. So it's going to just be M times X plus C for a simple linear um regression, but logistic, right? Not so MX times C. Okay, that gives us Z. We put the Z in the sigmoid, so I could have just put the MX times plus C in here directly. Okay, that gives us the prediction. Then we now calculate the loss, right? The loss is a negative log likelihood, which is this long equation. I could have used this long equation straight up in here, but let me just use a function. So in this case, we have Y. Y is the actual value, right? Y. And then P is the calculated probability. Okay. Of course, I forgot something. You have to load the values first. So yeah, but we have the Y and the P. Remember the Y and the P comes the X and the Y come from here directly. So that's okay. Um so you do this log loss and you get the value. Then you now calculate yeah, you can calculate the loss. You can add the losses to an array of losses. Okay. Can add the loss to an array of losses. Then um the next thing is gradients. So for you to calculate the gradients, the M is still the same thing, right? X times Y minus P. Where Y minus P, Y is a actual real value, right? P is the prediction. For C, there is no, you don't multiply it by X, you just do Y minus P. And then that's it. Then you increase the parameters with this learning rate. And you have a complete training loop. Okay. So even with the value of M and C that I started, right? So now you can see that my loss is blowing up. It starts off with minus 13, it goes up. So what does this tell you? What would you do in this situation? I think we had this similar situation last time. And I kind of explained in this case. Whenever you have loss blowing up like this, it's getting very negative. It means that oh, hold on. I missed something. The gradient has to have a negative, right? The gradient calculation has to have a negative. So if you go check it, let's just double check so that you can see. Um, well, so here's the thing. The gradient, the sign of the gradient must be the same as the sign of your prediction. So here the prediction was P minus Y. So the prediction is is plus, is positive, while the actual value Y is subtracted, right? But here it was flipped. So the prediction is now having a negative sign. So this is something that sometimes happens, right? Because the P has a negative sign, I have to negate it here. I could also do P minus Y, in which case I'll remove this negative sign. So, but whatever is the case, the sign here must match the sign of the prediction. Okay, so let me now run that. Okay, so we start off with yeah, I have to reset the parameters. But anyway, it was actually going downwards, so it seems like it was okay. But yeah, let's reset. The losses were very high because the parameters were also very high. I probably should have printed out the parameters, but they are dropping back down because I have reversed this um error here. If we continue to train for 100 epochs, now it goes up and it now goes to the it now goes positive and becomes positive infinity. So this looks like the learning rate is too high. So whenever it happens like this, it doesn't converge. What you would do is reduce your learning rate. So let's see if I reduce the learning rate a little bit more and see what happens. But it's already gone wrong. So I need to reset the parameters again. So I'm going to reset the parameters again and rerun this. The M and C has changed. I'm going to run this and it's still blowing up. Let me print the parameters at the end of this. Um, Probably need a very low learning rate because of how large log loss is. Log loss is typically very large. Um, let's, by the way, we don't typically use logistic for a single variable. It's still growing. You typically really use linear regression for a single variable. Maybe I have missed something. I need to check. X. Um, this is correct. Yeah, but it's still growing. Loss is basically going away instead of stabilizing. And it's probably because we are dealing with just a single straight line. The negative log likelihood is not like mean square error that is quadratic. So you know that it will always drop to the lowest value. If you overtrain in this negative log likelihood, you're always going to end up overshooting unless you have a lot of parameters. So anyway, yeah, I think I'll at this point it kind of yeah, it's stabilizing somewhat, and we can draw the line for it and decision boundary for it. So this is kind of very basic primitive. Typically, you will not do this, right? Um, so if we plot P against Y, I like to do this sometimes. So this is kind of trying to plot my prediction on this axis against the actual values. Okay, you can now see why it was going off the rails because Y is not constrained to zero between 0 and 1. So the this cannot really predict it. So this is not really a good example of the data you would use for this. The Y is going off the rails. You can see the Y has high values. So typically, if you want to do logistic regression with probability like that, the Y has to be in a range of 0 to 1, typically. But because you are already trying to do Yep, trying to predict probability. Um, anyway, it's kind of it's a probability to match. This should have been labeled data, right? So I used the wrong data set. This should have been labeled data to say, okay, yes or no, true or false, not numbers. That's what it should have been. So, but anyway, that's let's look at a real logistic regression case, right? Which is what we have here. Um, and then I'm going to talk a little bit about, there's a lot of equations here, but this equation is what we have already seen. So this is not very complicated. The only thing is that now we are now saying that if I was doing an example with a single value of X, right? But in most cases, when you're doing logistic regression, you are doing it with multiple values of X. So if you have to do a prediction with multiple values of X like this, you have M1 and X1, you have M2 and X2, you have M3 and X3, right? Of course, you still have the constant. So for this kind of situation, you are going to do a different calculation for each. In other words, for each coefficient, each M1, right? So first of all, for each of the x's, for each of the data points, you calculate the error. So the error you are going to calculate is going to be the total error for a data point is going to be the error that is contributed by, um, you know, predicting for y0, which is the first data point, plus the error that you calculate for predicting for yeah, this whole one is the loss rather for predicting for y0, right? The first data point. This is the error for the second data point and so on. So if you had like um a lot of data points, what I had here, if you look at this, we had about 20 data points here. It's about 20 of them. So you have an error for each data point, okay, up to n data points. So in this case, n was 20. So the total error will be the mean minus mean of that error, which is essentially what we did here. Minus mean, minus mean of this. That's a log loss. That is minus mean of this, right? So you sum all of them. So this is for multiple data points. Now, what makes this a matrix is that you now have the error for multiple data points. Then when you are coming to calculate the gradient, you now see that when you're calculating the gradient, remember that each data point is calculating a gradient. So let me pull data that we can, from another example, that, let's see if this one has, we have to have data that the y is a probability, basically true and false. Okay. So this is still the same y, so we cannot use this, but we have some values here which I will use as an example. Um, yeah, so let's take this as an example. If I were to take this and plug it back here, you now have a combination of x and y values in a tabular format. So, but you have, um, this is in a tabular format. So let me show you how this looks. Right. You have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, There are 20 data points as well. But these were all in, or maybe in order not to waste time, this, I actually had um, I had this which split it. So let me just use this at once. Okay, so you will get the true value of the y's. So if I run this, you now see that two sets, we have two sets of x's, right? You have this, this is x1, right? And this is x2. Okay, and then you have this set of values for y, right? This is y. Okay, and you can see that the values of y are either 0 or 1. So this is what you use logistic for. What I did before was not technically wasn't correct. So I have x and y. I'm going to separate it into x1 and x2 and y. So you have x1, x2, and y. So I could also separate it into x1, okay, x2, and y. All right. So you see x1 is this array, okay? We could actually extract this and put it in here. So it's easier for us to see and think about it. So this is x1. That's x1. And then this is x2. We can also extract, that's x2. And then this is y. So we have the three of them. I'm going to take out this section which I used to generate those values. So we now have x1 as an array of numbers, x2 as another array, basically vectors, vectors, and y, which is just the actual values. Okay, so that's definitely much better than what I have here. So I'm going to take this off. Now I'm going to do the same thing again, except that this time we have M1, right? And M2 because there are two x's. So each x will have its own M. And C is still there. C is a constant. So our Z is now M1 times X1, right? Plus M2 times X2. So this is still this is a multivariable linear regression. If I did not have um, if I had not had the sigmoid, we could have still done a linear regression, multivariable linear regression with this. So you now have Z, which is the outcome. You see that Z has negative values, right? And positive values. But probabilities don't have negative or positive values. So I have to effectively make this, let me take this off, make this into this is what we call logits, right? These ones that are kind of outside of the range of a probability value. And then when you convert them to probabilities using a sigmoid function, you see them here. Everything is now in the range of 0 to 1. And you can see 0.44 to 0.54. You can see our prediction is not very good. If I were to actually do a plot, so this is where we do a plot of X and Y, and it really helps. Matplotlib. And I plot P against Y. Okay. This should just be PLT. Scatter. You can do a scatter. So what you see here is the Y values. So you can see Y values are between 0 and 1. Um, but for the y values that are 0 and 1, right, the predictions are scattered. You can see the prediction, you have a prediction of 0.425, even though it should be predicting 0, and so on. So what this is telling you is that our predictions are not close to the real value. If it's close to the real value, when this line that is 0 should be a single point, so that the prediction should also be 0. And this line that is 1, which is the actual value of y, should also be 1 here, right? So when we train the model, it will be better. And you're also going to see that that issue we had of exploding gradients won't happen again, because that one was exploding because we were dealing with, yeah, this is the gradient. So let's go back to learning rate of 0.01, 100 epochs, losses. So the calculation is now M1 times X1 plus M2 times X2 plus C, right? Everything else is more or less the same. So we have a loss, and then we have all the losses. Then we will have two gradients for M. We'll have dm1, gradient for M1, which comes from X1, times the total loss, and then dm2, which is the gradient for M2, right? It's still the same. It's now going to be X2, right? So you can see the correlation. I'm doing this so that you can visually see the relationship, right? So each coefficient's gradient is determined by the actual variable, that it is affecting. So M1 is affected by X1. The gradient of M1 is X1 times the loss. The gradient, sorry, the gradient of M1, the gradient of M2 is X2 times the loss. And the gradient of C is what would have been X3, but in this case, X3 is 1. See, 1 times the loss. So that's why you see there's a uniformity there. There's a pattern. The gradient of C is 1 times the loss. So it's just y minus p times 1. That's why you could have easily written this as 1 times, y, and it will still be correct. That's really what it is. So we have those. So for you to now adjust the parameters, you can now adjust the parameters with the gradient. So same thing. For M2 and for C. And that is your training. So let's see how this goes now. So you can see here the loss is even increasing. So I need to check my equations. Loss is going from 0.64. It's actually increasing. It should be reducing. But then let's print this and see. Let's now print P and Y and see what this should be scattered. Okay, so um let's use a larger learning rate. Loss is still growing. So if you do this and this happens, it means there's something wrong. So you need to check. So let's fix this epsilon thing. I don't think that's the cause of our loss going crazy, but it's still good to do that. So normally, um, the best way to do this is um, np dot. Um, we have a function that allows you to basically determine the boundary. Well, we can use max so that um, after you have calculated a prediction, prediction should not be more than 1 minus epsilon, right? So the reason for this is, okay, so your prediction should not be more than that. And you can also do np dot mean. It should not be less than, um, yeah. Okay, so let's say P. I don't expect this to be the cause of the problem, but then um, the PN is just we have we are trying to prevent the P from uh, our loss from becoming negative or becoming infinite. The loss is actually not coming close, so there's a different problem here. Okay, that's a bit more complicated. I'm not going to do that yet. Okay, our loss is increasing still. It should be reducing. So we have a few points that have converged down here and up here, but um, okay, let's see. I need to troubleshoot this. YP. We actually have done this. So, well, okay, so we needed a lot of epochs. We needed a million epochs to actually get with alpha being the learning rate, we needed a lot of epochs to eventually converge. So maybe that is but here we had three values though, the DMs. But here it's diverging. So there might be something else going on there. Or maybe there's no correlation. Hmm. Okay, anyway, I'll run this. I'll come back to this. Maybe something will pop up because we don't have so much time left. Let me talk about vectorization. But I'll come back to this. Definitely something will pop up. Here we actually have a third factor. I think that's the main issue. We have three x's here, while we used only two of them. So there is no correlation. That is why it is actually regressing. There are actually three values, and then the y. One x2. Okay, m0 is the constant, so it's the same thing. So it's still it's still three values. So now there's a thing we call vectorization. If you look at what we did here, what I did here was I had a separate array for x1, right? And I had a separate array for x2. And then I had y, and I did them separately. So we started with 0 0.1, 0 0.1, 0 0.1 for the three values. And we have the z, m1, x1 plus m2, x2 plus c, right? And then we have the sigmoid, which is 1 over 1 plus np exponent minus z. Okay, we printed it here. And then we have the negative log likelihood, which is y times np log p plus 1 minus y times np log 1 minus p. Then we had a learning rate of 100 epochs. Let me increase the epochs a bit. Yeah, it's blowing up. And then um, now, when we were calculating this, right, you notice that we are calculating each separately. We are calculating each of the coefficients gradient separately for dm1, dm2, dc. And we are also increasing them separately. Okay, I think I've seen where I made the mistake. This should be minus. You always go in the opposite direction to the gradient. You always go in the opposite direction to the gradient. Yes, so this is another very good lesson why you shouldn't accept what your co-pilot gives you all the time. Yeah, so remember I had mentioned that the update is always minus. It's always a minus. When you have calculated the gradient, the sign that you put here should be the sign of the prediction. So if you did y minus p, then the sign here should be negative. If you did p minus y, then the sign here should be positive. So the gradient will always be correct and the same thing. But when you want to do the update, use minus. You should always go in the direction opposite to the gradient. So technically, I was going in the direction of the gradient. So instead of reducing the loss, I was increasing the loss. I was doing the wrong thing. But I didn't type that code because I was in a rush. I just accepted what Copilot did, and it gave me nonsense. It gave me plus. So that's why I wasn't converging. So now we are converging. I can actually I can increase the epochs further, 1,000 epochs, and run it again, and it goes to 0.1. You could actually, if we print this at this one, if we print it at this point, you see that they are now migrating towards this point. These ones are migrating towards this point, and these ones are migrating towards this point. And if you look at what I did before, we actually needed a million epochs at learning rate of 0.01 to be able to converge something. So I'm going to run it a million epochs, but I'm going to do a slight improvement or change of my thing so it doesn't print every time. So it will just print only every 100 or every 1,000 epochs, right? So please, again, be careful when you are accepting pilot's recommendations. I'm going to go to a million epochs. Um, okay, I'm going to go to a million epochs. 0.1 is a good learning rate, so I don't need to go to a million if it is 0.1. I can just go to 100,000. Okay, and let's just rerun everything. Yeah. So while that is running, I will complete. So you can see loss has gone down. Now it's none. So it's gone so low. It's gone into the negative. So that's why this is where the epsilon comes in. The epsilon would have checked this and allowed me to keep trading or maybe flatten out at this point. But you can see after training, all of them have clustered around here. So the predictions are close to the actual value. Okay, so um, but the point I was trying to make was we were doing them separately. So here in this lecture notes, you will see that we had M0, M1, M2. So instead of using C, I used M0 for the coefficient that doesn't have any independent variable, basically the constant. But for consistency, and everything else is the same. All of this is the same, basically, what I just did. But here you can see that we were calculating each gradient separately. This one didn't have the x because, of course, it's a constant. This one has the first x, which is x0, and this one has the second. But this time around, instead of me taking each x separately, I stack the x's into a matrix. So I only pick the first row. So this is the first row of x, or the first column of x, really, because the first row is the first data point. But the first column of x, right? So this thing we call raw residual is the name that you give to the difference between the predicted value and the actual value. That's a raw residual. So you always use the raw residual to calculate, or the residual, that's another name for it. You use to calculate the gradient. Now, this was doing it three separate ways. The interesting thing is that I can now combine these three and do it in a single go. In a single go, instead of separating it. I could just do DM, right? That's even because we have three different M's, right? But you could have just one M, and that's where the vectorization comes. So let me explain that vectorization. So vectorization is saying this. Let's assume that you have three data points. These are three data points, right? The three linear equations, right? Now for each of these basically, it's not three linear equations, it's the same single linear equation, but you have three different y's, you have three different x's, you have three different x1s, three different x2. Each of this is a single data point, a single point on a graph. Think of it So you're trying to come up with a single equation that will, uh, s- um, that will fit these 3 points. Now, each point has three features. In other words, they have x's, three x's. You have x1, x2, x3. So you have three x's, you have this one y, basically. And if you look at the c, it's also um, a constant. Then each x has the parameter, the coefficient. You will notice that even though the three data points are different, but they are governed by the same parameters. So it's the same m's. It's the same m1. It's the same m1 across this. So all the x1s have the same m1. All the x2s have the same m2. All the x3s have the same m3. That's what this notation means. It also means that this one with a bracket is data point. So you have three data points where each data point has three features. Uh, A feature basically refers to the independent variable. So you can then take all of this and represent it with a single matrix or a single matrix equation. That is what we mean by vectorization. That single matrix equation is basically saying you extract the three data points, which are the y's, the three y values, the three actual values, and you have them here. The y of the first data point, y of the second data point, and y of the third data point. And then you will have the second part of the equation, the one on this side of the equal sign, you can decompose it into two parts. The first part is the vector of parameters. So this is what we call the parameters in machine learning. These are the things that you are training the model. These are the weights that you are adjusting. These are the coefficients of the equation. The same C will govern these ones. The same M1 will govern these X's. The same M2 will govern these X's, X2s, and the same M3 will govern this. Then in this matrix now holds the data. This matrix represents the data, where each column is called a feature. Each column is called a feature. So let's assume, for example, if you look at the original data that we used, the DMO, DM1, DM2, these are the we calculated the gradients. But those gradients are tied to specific things. If you look at the original data that we actually decomposed, those data mean something. It could be maybe the weight or the height of someone, or if you are trying to predict the housing, the cost of a house, it could be the size of the house. So one feature represents one thing that has or that contributes in a way to the total prediction or the value, the final prediction you will make. So you now see that the X1 could be, so you have three data points, right? This one could be the height of the uh, James, right? This one could be the height of John, and this could be the height of Mary, right? But they're all heights, so that's why it's feature. So the column represents the feature, the heights. The row represents the three individuals that you are looking at. This second column could be another feature, maybe the weight. So this could be the weight of John, X2, weight of James, X2. So you have X2, 1. X2 refers to the feature. 1 refers to the person, the individual, the record, the data points. These all refer to the same thing, right? X2 is the weight, but of another person. So 2 is the second data point, or the second person, or the second record, or the second row. This is how you interpret this. X2, 3. So again, 3 represents the third person, but X2 represents the second feature. So the 2 subscript represents the feature number, while the 1 superscript represents, or the superscript represents the data point or the individual. So that's why you see that this one is The same individual, but three features, X1, X2, X3. And those three features could be anything, right? But the X1 features are all the same feature. It could be color of the face, shape of the, face, height, weight, and all of that. Then the parameters are the things that would now weigh against this. So when you now take this decomposition, so you see we started off with a system of equations, right? Each equation represents a single entity or individual or row or record or data point. Each equation. So each Y is the prediction you are predicting for that person or individual, maybe the BMI or how many years a person will live. So that's the prediction, or that's well, the Y's are the true values, not the predictions yet. Then this thing you are trying to predict is made up of a linear combination of features and parameters, or features and weights. That is how it is then decomposed into this. And then this is now simplified representationally into just three things, where Y now represents all of these Y's. So when you see Y like this, a vector of all the true values that you are going to train your model on, the labels, that's what it is called. Then this big X, why it's big is because it's a matrix. So in machine learning, the convention or the mathematics of this is vectors. You typically use lowercase alphabet for vectors. A vector is a one-dimensional um, data structure. You can see it only has one column. It's only one column, right? It has only one column, three rows, one column. So it's a vector. By the way, the orientation doesn't matter. A vector could also have one row and three columns. But as long as one of the dimensions has one, right, it is a vector. And vectors are normally represented with a lowercase y. So that's why this W is also a vector. It's lowercase because it is just a single column, right? Even though technically it's not a single column, it's a single row, right? But then there's a transposition there. Then X is uppercase because it is a matrix. It is two-dimensional. It has rows and it has columns. So we have decomposed this equation into an equivalent equation that if you actually look at it, it is the same thing. The only difference is that now Y is now referring to all the Y's, right? Not a single Y. It's referring to all the Y's. And then you also see that W is a parameter. It's referring to all the parameters. So take note that all the parameters are the same. The C is the same across all of them. The M1 is the same. The M2 is the same. M3 is the same. That is the weights. And that's why we use W, weights. Sometimes theta is used. And then the X is the data, the inputs. And it always comes in a matrix because you will have rows for each data point, for each record, for each individual, right? And then you have columns for each feature. So this is very important to explain so that when you see something like this, you know that we are not referring to just single values. We are referring to the entire data in the data set. Particularly when you see X like this, you know that X actually refers to your entire data set, right? That you are bringing into train. And then when you see Y as a single vector, Y represents a single list of label data. But you can also see Y as uppercase. In this case, Y actually refers to also a matrix of values that you are predicting. So you may want to predict categorization. We'll look at that when we look at more advanced methods like neural networks, right? So you are predicting multiple values of Y. And you have Y1, Y2, Y3. So you have Y1, Y2, Y3, which is three different features you are predicting. But for each, you have a different individual or data set. So these are one, the first person, the first data point. These are two, the second person, right? And the second data point. This is a convention that you will see And that's why I said at the beginning of this class, I said that the mathematics is mostly the convention. Once you understand the notation and the convention, then the mathematics becomes easier. So that is what I just explained is this. Y basically, this should actually be a lowercase y, not an uppercase y, right? Should be a lowercase y. So the y represents the whole um yeah, the y represents this vector. X uppercase represents the matrix of all the data that you're training on, and W represents the weights. The only thing you are training or adjusting is the W, which is made up of all of the parameters. So once you understand what Y means in a vectorized form and what X and W mean, then the matrix comes in. So you now see that the vectorized representation of linear regression is the Y hats. This time around, the Y is the entire Y, the entire vector, equals X theta. So X is still the same X. And this time around, instead of saying W, we're using theta. So they can be interchanged. And then you can now see the function for the mean square error. It is still X theta. X theta is still Y, Y hat rather. So this is just Y hat minus Y, which is the um that's a raw we call it raw residual. I keep forgetting that word. So that's a residual, right? A residual is just a name for the difference between the predicted value and the true value. Okay. And we now square it. This is element-wise squaring, these double pipes. And then we divide it by the number of elements in there. So this is a cost function. This is what we have already seen, right? It's y minus y hat, mean square error, basically. This is mean square error. The gradient, right? This upside down triangle is basically partial differential, right? But it is used to represent the entire matrix. So again, x theta, which is y hat, the matrix version of y hat, minus y, which is again the matrix or vector version of y. Now we have to do X transpose. So this is where the X transpose makes sense because X, remember, X is this, right? X is this. You have to transpose it. Otherwise, you will not be able to do this matrix multiplication. Unfortunately, I don't have time to kind of explain that, but that's what that does. So, and then the gradient update again is represented that same way that you can actually update every single parameter at a single go by just taking the X transpose. This X transpose X0 minus Y divided by N is the same thing as this. So it's basically the gradient. You divide the gradient. The gradient is going to be for every parameter, there will be a single value, right? Even if there are a million data points, there will only be, let's say there are 12 features and a million data points, right? Right? There will be 12 parameters and there will be 12 gradients. The number of gradients always match the number of parameters, right? So that's why you need this transpose. It will remove that and then you divide by n. So you get the gradient. You then multiply each gradient by the alpha, which is the learning rate, which kind of then influences how much the gradient affects your parameters. And then you subtract. So remember that subtraction that I just did. I missed it, right? So you subtract that value from the original parameter and you use that as a new value of the parameter. What this arrow means is put it back into the parameter after subtracting it. This is the mathematical notation. So this is a vectorized format of the linear regression. This is a vectorized form of logistic regression. Remember, the only difference is two things between linear and logistic. The first thing is we add a sigmoid function. The x theta is still the same. This x theta is the linear combination of parameters and weights. Basically, x1, m1 x1 plus m2 x2 plus m3 x3. That is what x theta is, right? So it's always going to be constant. But you now pass this x theta through the sigmoid function, right? For logistic regression. And then that's all. It gives you the probability. And then this probability, you now use the negative log likelihood. Same thing, right? For each data point, because you use data point to calculate loss. The loss is per data point, while the gradient is per feature, right? So the loss is per row, while the gradient is per column. So you have the yi lean pi, which you already saw, and I already did a breakdown of this, the piecewise negative log likelihood, binary cross entropy, right? Same thing. And then this gives you that. Remember, you always have to have the negative sign. That's why it's called negative log likelihood. Because the lean of a number that is less than 1 is going to be negative. So you have to use a negative sign to correct it so that the loss will be higher when it is further away from what you want. And you can see that this is the only two differences. It has a different loss function. And secondly, you pass the linear combination through a sigmoid function. But the gradient equation is exactly the same. The gradient is exactly the same. It is a residual times x transpose, the mean of that. So the gradients are the same, both for linear and logistic regression. And the update is also exactly the same. You just take the gradient, you multiply by the learning rate, and you subtract it from the previous parameter, and you use it to update the new parameter. So this is the um, vectorized implementation. Now, when you are writing the code for it, you find a vectorized implementation. I am now doing that same logistic regression now, but I'm using vectorized implementation. Now, look at the difference. The difference is that the W is, you get the dimension. I'll explain this a bit more, maybe when we meet again. But you see that there's no loops. The only loop is a training loop. You see that the gradient is a single function. We didn't do three different gradient calculations. We did a single gradient calculation, and we did the x transpose dot p minus y, which is a key element. You need to remember that x transpose, right? Dot. Remember, x theta is either y hat if it is linear regression, or x theta sigmoid is p. So x transpose dot p minus y. That's what we did here. Okay, x transpose. So in NumPy, you can use x dot t. You use dot capital T to do transpose. And then you use a dot product, right? The dot means do a dot product. Some languages like PyTorch, when we get to PyTorch later, they call it a mole or matmole rather. And then p minus y, this is a residual, which is again a difference between my prediction or the model's prediction and the actual value. And then you now see it divides by n. So we could have also done mean or something. The loss is still the same thing. You see it's np dot mean y times log of p. The epsilon again is to prevent division by 0 or log of 0, which can be problematic. If you see what we did here, I got nans because I got to 0 and I started doing log of 0. So it's telling me it's invalid value, divide by 0 encountered in log. So essentially we are doing log of 0, which is not correct. So that's the essence of that epsilon, to prevent this error. So your model can continue training instead of collapsing into nans. So that's epsilon. We'll talk more about that as we keep going. And this is it. So if you look at this training loop, it's the same training loop as we did here. But you can see that I didn't need to do 3 of this. I didn't need to do 3 gradient calculation. I didn't need to do 3 updates. Now, where this matters, if I was just doing 3 like this, it wouldn't be a problem. You'd be asking, okay, why do I have to go through all that difficulty if I'm doing 3? 3 parameters. But what if you were doing 500 parameters or 1,000 parameters? Or like large language models of today that are billions of parameters. Would you list all of them out one by one? No. That is where this vectorized approach becomes useful, because whether you are doing 1,000 features and therefore 1,000 parameters or five, this equation will work exactly perfectly in both situations. That is the value of vectorization. So I hope this kind of gives us a bit of introduction. I needed to introduce that topic so that you can understand vectorization, and go and take time to study more and understand it, read more about it. It is very, very important to understand representation of information in machine learning. Later on, I'll talk about things like tensors, which is now, you're now looking at multi-dimensional representation. Vectorization is just like the second dimension or the third dimension. In fact, it's just the second dimension, right? But when we start talking about tensors, you now need to learn how to visualize data in your head by looking at, you know, the numbers. You now we'll start looking at dimensions. We start talking about dimensions, 5 dimensions, of when you get to multi-head attention, you're going to look at like 5 different dimensions, which is difficult to visualize. So that, I think, brings us to the end of this class. Take some time to look at vectorization and understand how it works. It is very important. Are there any questions? Okay. If there are no questions, I will round up, and then yeah, so we've talked about training. Training is the same, right? Um, it's the same approach. So I hope we have. I hope the class was exciting. Maths is exciting, right? Any questions?